All right, welcome back to another Mr. MathWell video. This is Chapter 10 in Pre-Calculus 30, and we're talking about function operations. We're getting near to the end of this semester, and function operations. Okay, so the first thing we're going to take a look at here in 10.1 is sums and difference of functions. So I have this little clip up here to the right. You may recognize this if you've taken a physics class or a physical science class. You've experienced wave superposition. Right? So think about that concept in science, wave superposition. What happens is when you have a wave, which represents sort of a sine function, think of it like that. When you have a function like this, a wave, it meets another wave, and if they meet crest to crest, then the resulting wave is really large, right? Because those values of those waves add up to each other. And when you have a trough and a crest meeting, well, they cancel each other out, and that's like a node, right? That's a zero. So in this picture, you can see the really bright spots here, maybe like this. This is maybe a crest and a crest meeting, right? The really dull spots here, the other parts here maybe are where a crest and a wave meet. Tougher to tell here, but you have those sort of things happening. So sums and difference of functions. So if we take a look at this first part right here, let's take a look at an example where we have f of x is 2x plus 1 and g of x is x squared. So what you can do to add the functions, all right, is simply take a look at the values of each function at a given x value. So let's take a look at this. At x equals negative 2, where is this on our graph? And I have all three of these graphed right now. So at x equals negative 2, the 2x plus 1 graph is equal to negative 3, right? You just plug the x in there. So here it is down here, negative 3. That's the first graph. The second graph, g of x, is x squared. And when you put negative 2 in for x, you get a value of positive 4. So here's positive 4, okay, the turquoise one. So we've got the blue one and the turquoise one. If we were adding these functions, first of all, the resultant function would look just like this. That is a sum of this plus this, right? It's just a new polynomial function, which actually is a quadratic. And so the values at x equals negative 2, if we have negative 3 and positive 4, if you add those up, you get positive 1. So the red graph is the resultant graph. And you can just do that for every x value. To pick an x value, like let's say x equals 1 here, okay? So on the x squared graph, 1 squared is 1. On the 2x plus 1 graph, when x equals 1, you have a value of 3. So it's 1 plus 3, it's 4. Again, that goes on your new graph. And you just do a series of additions and you connect all the points, and there you have your new graph, okay? So you simply add the two graphs together, and it's really, really easy. 10.1 is really easy. So look over here, the sum of functions. I'll zoom in for you over here. If h of x represents f of x plus g of x, just a sum of two functions, you simply add them together. Add the equations together to make one big equation. That's your h of x. To find the points of h of x, you evaluate f of x, and you evaluate g of x, and then you add those two numbers, and that's the value of h of x. Same as for difference, okay? So difference is exactly the same. You can subtract functions if you want, and that'll obviously be a different graph than if you add. There's other notation here that you want to take a look at. F plus g, brackets of x. This is another way of putting that, okay? All right, so let's keep going here. 10.1. I put up another example here that's maybe just a bit trickier, and we have to take into account the domain as well, okay? So let's say we had a function like f of x is root x minus 1, and g of x is x minus 2. Well, first thing we notice is that there are restrictions for the x value, x variable here for this function, right? If it is anything less than 1 makes this value under the root sign negative, which is no good. So we have to understand that there is a restricted domain for this function. And that actually is a big deal when we add it to another function. Even though there's no restricted domain for this function, when we add these two, do you notice on the resultant function here that this new function is also undefined where one of the functions was undefined? Do you see that? So that's a big point there in 10.1 when you're looking at the domain. Here's the graph below here. So if we take the root x minus 1 graph, that's the blue one, okay? Notice that it doesn't exist on this side of x equals 1, right? This turquoise graph right here, this does exist everywhere. That's fine, XER, no problem. But the resulting graph, the red one, can't exist where this one doesn't exist. So it has to start at the same place this one does. So you have to take into account, if it's undefined in one of the functions, it's going to be undefined in the combined function. Okay? And everything, you do everything the same way. Take an x value like 1, right? And this one is 0. So that's 0 there. What is it in the next one? It's -2 right here. So when you add those two, oops, are we? Oh, we're subtracting these. Look at this. We're subtracting these. Sorry, this is a subtraction example. I missed that. So sorry. We have 0 minus a -1 here. That's +1. See, 0 minus a -1 is +1. My bad. I didn't see that. But yeah, we are subtracting x minus 2, which means minus x minus a -2, or minus x plus 2. So that's an example of subtraction. Okay. All right. So there's the key ideas. Just simply add or subtract the functions as normal, but just make sure you remember the domain, right? If we have a restricted domain, then the resulting function is going to experience that same restriction. Okay. 10.2. Products and quotients. Well, if we can add and subtract functions, we can also multiply and divide them. Here's some notation that you want to take careful note of. F of x just right beside g of x, that means multiplying. Also, if we have a dot here, just like in 2.5, that means multiplication, so that's another notation for multiplication. And here's your quotient notations as well. So if we were dividing functions, no big deal. We might have some crazy functions, yeah, we might. But you know what? If you take a look at one point at a time, one x value at a time, and then do this value divided by this value, whatever, then you're going to be good. So let's take a look at this one on the right. I have some things pointed out here for you. If we take a look at x equals 5, okay, so here 5 minus 1 is 4, the square root of 4. That should be 2. Is that right? Look at that. It's 2 on the blue graph. What about this one? 5 minus 2 is 3. Okay, so we should have 3 on the I guess that's the red one, g of x, yeah, 3, okay. So now we simply, at this x value, to find the multiplication, we just simply do 2 times 3. And that's why this is the 0.6 on the new graph, okay. So you just multiply the values. All right. Dividing, one thing you have to remember is if you're dividing by 0, that's no good, right? So that's going to give you an asymptote. And notice here that the resultant graph, this turquoise one here, right? It's a rational function, which is great, but it stops dead right here. Why? Because of the domain of the blue one, right? So it does not continue. It doesn't continue up like this or whatever. You see, it doesn't do that because of the restriction on the domain. Okay. So when you're dividing, make sure that this g of x, right? That can't be a 0. It's no good there. And other restrictions as well. Okay. So, all right. So this one is determine the equation. Okay. Well, if you're given, g divided by f, right? You can simply write it just like this. H is g divided by f. And then, of course, just like we did last chapter, we can factor and simplify, note restrictions, and then sketch the resultant function, which is the graph. So take a look at this. This is a good example of how to determine a function of when we're dividing functions. Make sure you remember your rational function skills from last chapter. Okay, and here's the graph over here, of course. Notice again, just as a review from last chapter, that because this x plus 3 is divided out, the -3 is going to be a hole, right? A gap discontinuity right there. That's the gap. And for the x minus 2 that remains there, that +2 restriction is going to be this asymptote, vertical asymptote, right? Okay. And then, of course, I just have this down here too. Remember that when you divide, the denominator can't be equal to 0. So even though individually there's no restrictions on each of these, right? There's no restrictions on the domain for either of these functions. When you have a division, notice that the f here, f of x, can't be 0. So that f of x was this one, right? So we cannot have -3 and +2 in our domain, and that's why it just shows up there. Okay? So the domain can't be -3 and 2, and the range can't be whatever -3 gives you in the final function, and whatever 2 gives you in the final function. And of course, these numbers right here for the restriction on the range comes literally from putting x in and this x in and finding out what those values would have been, sort of thing. Okay, so that's a little review. That's 10.2, and here's the summary for 10.2 if you want to pause and read that. Multiplying and dividing functions. All right, we're moving to 10.3. This is the final section. This is a short chapter, and composite functions. Composite functions are basically one function inside of another one. Okay, so you have two functions. You have an inner function, small inner function, let's just say this fist, and a large outer function. And literally the inside function is inside the outer function. So we have a composition of functions here. What is it composed of, right? So yeah, and the notation is a bit funny. See, just take a look at this here. So this means f of g of x. That means that we have g of x inside of our f of x function. You see how it's tucked inside there? That's what that means. So let's take a look at this. The g of x function is 2x minus 3. You see that over here? The f of x is root x. So we put 2x minus 3, that's what g is, in the f of x function. Well, it goes in where the x is. So it comes out to this one right here. Very, very important. Okay, so if you can rewrite those functions, if you can rewrite a function like that, that's really, really important. Okay, and of course, I've just kind of showed you that over here on the right. This is another way of looking at it. You may find this helpful, you may not, but if we have an x, okay, the x when inside the g of x looks like this, 2x minus 3. You see how the g of x turned the plain old x into this? And then this right here is now the input for the f of x. So now this goes inside f of x, which creates this. Okay? So one into the other. Okay? All right. Now, one of the ways we can evaluate a composite function is, and this is probably the easiest, is you start at the innermost function. Okay? The innermost function. This is calculus verbiage here. Okay? Innermost. I use that a lot when I teach calculus. The innermost function. So look at this in A, the g is the inside function. So what we're going to do to evaluate this is we're going to start by evaluating the g of 3. Whatever g of 3 is, we're going to evaluate that. So now, here's my work down here, you see. So g of 3 is where we're going to start. G of 3, well, there's g, and if I put 3 here, I have 3 plus 6. You see that? Okay. So that 3 plus 6 becomes a 9. Now I move outside, and I do the outer function. Now 9 is now my input for the f function. And what is f? Well, f is 4x. So that's 4 times 9. My answer is 36 there. Okay? So one of the ways of doing this is evaluating the innermost function and then using that value that you get as your input for the next function outside. And really, you could have a number of functions, right? But we're only really dealing with 2, I think, here in this chapter ever. So I put down c here. Look at c as h of 2. That's kind of funny, hey? But you can put one function inside of itself, right? So x squared can go inside of x squared, and that's no problem, right? And so we just evaluate the 2 and so on. Now the second method, there's another method here that may be helpful as well. I'm just going to go over really quickly the 2 methods of evaluating this. The first one is, actually the second one that I wrote down here, this number 2, is just what I explained to you. Evaluate the inner function first, and then put that value as the input for the outer function. That's sort of method number 2. Method number 1 is it's a little bit slightly different. In method number 1, what you do is you just take a look at these functions themselves, like right here, and you combine them appropriately without putting the number in first. You just use the x's. So if we're talking about here, g of h of x, that means I need to put h of x here inside the g of x. So you should notice that this x squared has to go inside the other function. So it's going to become x squared here plus 6. And really it's slightly different, but if you evaluate, state the new function first, then you can go ahead and put the original x into that new function, and boom, you've got your answer right away. Okay? So again, you can evaluate the inner function and then use that answer for the outer function, or you can slam both functions together right away and get a new expression for the the composite function, and then just put your x value into the new expression. Slightly different, but there's your two different methods from there, okay? I should note this notation here is really important, that you'll see this lots. F of g of x can also be written as f circle g. Now, yeah, sometimes they say circle, or this just means f of g of x, f of g of x, you know, f of g of x, same thing, just this notation here. And I'm literally, I've heard it said f circle g of x, whatever. So you can say that, I guess. Sounds kind of funny now that I say it like that, but it means f of g of x. So think of that as an O, not a multiplying. It's not multiplying, it's different. The multiplying is the solid dot, the composition is the circle. Maybe that's why circle. Okay, here's a different type of question I want to go over with you. Again, just two more examples here in this review video. But this one here is a question you're going to get. It's going to give you h of x, and it's going to tell you that h of x is a composite function. And you have to determine what the two functions are. So this one is the inside function, isn't it? Because g of x is inside, and this is the outside. Okay, well, how does that help us? Well, we have to look at f of x as something, you know, the entire expression is f of x. And g of x is going to be a piece of that. So you want to look for things that seem to repeat. And for this one, I hope that you see that inside this larger function, we have this cubed root of x that shows up twice. You see that? Okay, and there's your hint right there. So the inside function, g of x, is going to be this one that is tucked inside, the cubed root of x. That's the inside function. So g of x is, what is that? Cubed root of x. I should write that properly. Cubed root of x. Got it? And then the outside function is going to be your, this is going to be your f of x. And so let's replace this with just an x. See? Just an x. So f of x equals x plus 3 over 3 plus x. Okay? All right? I'll take a moment, let that settle in. Hopefully you understand that. But it's just sort of recognizing what is the piece that's inside that could be represented as a separate function altogether. And it'll be a piece that repeats. So, and you'll be able to pull that out and replace that with an x for the larger function. Okay? All right, the last example I'm going to go over with you is example number 5 in your textbook. I can't remember what page this is on now. It's 10.3 something, but I just thought we don't do too many word problems. I just focus on skills in a lot of these review videos, so I'm going to do a word function so that you can see how that pans out as well. So this one says a spherical balloon, that's going to be important actually, spherical balloon is being inflated. Okay, the balloon's radius is r, it's in feet, after t minutes is given by this, so r equals the square root of t. Okay, A says express the volume of the balloon as a function of time. So we're looking for v of t. That's what we're looking for. Okay, well, we may not be able to go there right away though. Let's first of all think of what is the volume of a sphere. Here's the sphere in the picture. Here's the balloon. Well, the volume of a sphere, if you don't remember this, you might have to look it up, but hopefully you might remember it's 4/3 pi r cubed. Okay, 4/3 pi r cubed. The volume of a sphere. And so that's in terms of r, isn't it? Okay, and that's what we know. That's maybe the first that comes to your mind. But what you have to do now is we can't have this in terms of r. We don't want v of r. We want v of t. So now you have to put the r function, see, the r function inside the v. See? So I need to replace this part, don't I? Okay, so that's going to make this over here. V equals 4/3 pi. Now what is r? Square root t cubed. Okay, which finally gives us now a function of t. So now I have the variable inside this is t. This is volume in terms of t, and that is 4/3 pi. And I'm going to write this as t to the power of 3/2. You okay with that? Because this square root is like a 1/2. Okay, cubed. So 3/2. Okay, so there is your function for A. All right. Now B says, after how many minutes will the volume be 4,000 cubic feet? So the volume is going to be 4,000 cubic feet, and we're looking for T. We need to solve for T. So just for time's sake, I do have that over here somewhere, right here. And so V of T is 4,000, so I'm going to put 4,000 here. and we're going to solve for t, which we've done before in the last couple chapters. So that's no problem. And I kind of did a bunch of steps at once here. All right, I did 3, multiply both sides by 3 to get 12,000. Then I divided by 4. 12,000 divided by 4 is 3,000. That's this up here. Then I divided by pi. Here's divided by pi. Then I took the cubed root to get rid of the cubed. Okay, cubed root. Actually, I squared first, I guess. I squared both sides to get rid of this, and then I took the cubed root. So that's just a bunch of steps at once. You know, that hopefully you should know how to do that, but that would be another video if you need help with that. But t should come out to now when you just plug this into your calculator, 96.97 or 97 minutes. Okay. And of course, you look at the question, t is in minutes. So whatever the number is for t that you get, that means it's minutes. Okay. And r, the radius, is in feet if you're asked a question about the radius. Okay. All right. So here's just some key ideas for 10.3. And functions can be composed. 2 functions can be composed. One can go inside the other or vice versa. Okay. Method 1 is substituting a value into the inner function first, then that result into the outer function. And method 2 was slamming both functions together, simplifying them, and then put your input value in. The first x, the input value right there. Okay? And remember the domain. Okay? If there's any restrictions on any of the functions, you have to consider that for the final function, because that domain is probably going to be out of bounds for the final one too, right? So just remember that. Okay, that's chapter 10. There's your review video. That's the whole chapter. Hopefully that helps. If you want to review any of that, please look at the full lessons that I have on YouTube, Mr. MathWell, PC30 10.1, PC30 10.2, PC30 10.3, and then this review will be up there as well. So good luck in your test. God bless.